So welcome you all again. So I'm now going for equality for of survival function. So again, this is again this disclaimer. So now see, now while we talk about survival analysis, basically the two way the survival analysis can be done. Obviously, one thing is that preparation of the data or by graphical explanation of the data, or makes presentations of the data by preparing the cards, graph, plot, and secondly by the numerical results like p-value, percentage comparison, median survival. So these are the two way any kind of work. I would say that any statistical applications applied in two directions basically. Here, this is survival analysis is also not exception. Here also we are having the survival curve comparison and as well as the some p-value and results or numerical validation. So why this curve is very much important, because it's give you the overall idea, overall pictures of that of the study and work, and that is very much important. And easily you can get an idea about what's happened to the treatment. So or between the treatments, which treatment is better and which is not. That is very much eventually meaningful to have the survival curve comparison. So survival curve comparisons curves, let S cap T is a estimate about the populations through the sample. The challenge is to quantify uncertainty on it. My apology, my sentence, it's a spelling mistake is there. It should be challenge, not challenge. So anyway, so once we are talking about the S of T, and then once we are talking about S of T, then the estimate of that S of T is called a S cap T, and the intention is to quantify the uncertainty on it, or the what is the probability difference between these two groups. And there are two ways that the survival curves can be compared. One thing is the generalized Wilcoxon or Gehan test, and another one is the Lagrange test. So what is the fundamental hypothesis behind to apply any curve comparisons or graphical comparisons on that? So null hypothesis and alternative hypothesis, here also it stands, and it says that S1T equals to S2T and S1T not equals to S2T. What is S1T? Let's say you are having two group of treatment 1 and treatment 2, and it can be one treatment, one could be let's say chemo and treatment 2 could be radiation, or treatment 1 could be chemo, one kind of cisplatin and chemo, and another is the cetuximab, any combination of the two therapy. So basically this one, S1 and S2, these are saying the two type of treatment. And for that treatment, the suffix these S1 and S2, these are saying about that two type of treatment, and corresponding these two type of treatment, what is the survival functions value that you are going to estimate, and that we are going to make the comparisons, and that we are going to make with the null hypothesis. So basically, our null hypothesis says that if you give one kind of treatment, one type of treatment to a group of patients, and another type of treatment with another group of patients, and over the time, because S of T, over the time, their durations or their survival probability is going to be same. That is a fundamental applications of the null hypothesis. And alternatively is saying that is different. So this difference could be anything. So if it says that S1T higher than S2T, that's mean people treated with the S1 group are having better survival than S22 group. If it says S1T less than S2T, that means says that people treated with these S2T groups are having better survival than this S1T group. But remember, one thing is very important. We are talking about T, and T is basically the time, and time is dynamic in nature. One of the fundamental challenges you always face here, that if you talk about, if you freeze T, let's say T, we talk about T is equal to 1 month. So if we talk about T is equal to 1 month, then what happened at the end of 1 month? What is the probability of survival of at the end of 1 month? And then what is the end of 1 month from both the group? That would be compared. That could be one. It might happen that one month, at the end of 1 month, one group is doing better as compared to another group, or vice versa. So T is very, very face the challenge over here. In other kind of hypothesis testing, we never face this challenge, because other kind of hypothesis testing never comes with the time as an effect. Time as a function and effect is always plays role here. So that's why now again same issues can arise as 2 months, 3 months, 4 months, and all time point. So that's faces real challenge. So how to make the hypothesis and how to come to a conclusions and how to make the interpretations over that. So that's why the survival comparisons is important, and it's not only this simple at time point it's overall time point wise you have to make the comparison. Now see, this is a curve. So if you say that there is a two groups, one is given, the red color is given as a placebo combinations, and blue color given as a pembrolizumab combination. So obviously those who are given placebo combinations are having poor survival as compared to those who are given with this treatment like pembrolizumab therapy. Now see, the questions comes here. If you talk about 1 month interval up to 1 month, both therapy were doing same, because those are these green color, blue color and red color, they are overlapping with each other. So it says that they are doing the similar way. There is not any difference on it. But slowly you say that blue is making difference on that. Now questions comes, are you talking about effect of treatment over control at 9 months, at 6 months, at 3 months, at 12 months, at 15 months, 18 months, or overall or at the end of 21 months? If you say at the end of 21 months, there is a huge disparity is there. But if you talk about after only 3 months, hardly any difference. After having 1 month, no difference. So now, since if the experiment is now the inpatient point of view, it makes very important, because we are dealing with the individuals and we are giving the patients with the costly drug as compared to the existing or control or very nominal chargeable drug combinations. Now questions or patients party or patients may raise the questions to doctor that if I get that if I get the treatment, what is the chance of getting me to be alive beyond 5 months or beyond 15 months? Because the person is going to purchase the prescriptions or consume the drug, and simultaneously it's a cost-effective way, because they are going to pay huge money and they are expecting that their life will be expanded. But what is the chance that reality it would happen? Those are going to get past this 1 month crucial period or 2 months going to crucial period, because see, up to 1 month or 2 months there is hardly any difference. So those are going to pass this first and second month's difference duration. They are going to get benefit over the period as compared to. So if the persons are going to get only 2 months up to 3 months, that this therapy, there is no hardly difference of this costly therapy as compared to existing or the very, very simple cisplatin or something like that. So that's make huge impact of this survival curve comparison, up to what extent the person is going to be benefited. And that questions giving the answer is very critical. We never get that answer. So we give that if you survive more than 5 months, then your chances to having survival is beyond or having high than that. That sort of answer as a clinicians are supposed to give. Okay, so that is very crucial questions altogether. Now, this is the one kind of curve is presented here. It could be different types of curves together. Now, life get quite complicated while you say that in low and high doses given, there is no difference in initially and later also no difference, but meanwhile there is a big difference. Now question is come, so should we treat the patients with the NLR low or should we go for NLR high? because overall there is no difference between NLR low and NLR high after 84 months. But if you talk about 24 months beyond or 36 months beyond, up to 36 or up to 48, obviously NLR low is doing better than NLR high, or even this peak up to 12 months. So NLR low is doing fabulously better than NLR high. Another kind of curves may occur like this, where we are having no directions. Sometimes NLR low doing better than NLR high, and sometimes NLR high doing better than NLR low. So overall, we can make a conclusion that both of them are equal. However, they are not overlapping each other, but some zigzag line is coming, and one thing is higher and another thing is lower, and that makes our life complicated to make a conclusions by looking the curves. So see, another curves is there. So this is another survival curve. So here both of them align together, and there is no difference between high and low. Sometimes low is doing better, and there after they overlap with each other, and again NLR started to doing better, and after that NLR dropped down and NLR high was doing better. So basically, while you are talking about the survival curves, you are talking about this y-axis as a probability, and the low higher the curve is having, the better the survivability is. Okay, so here see the probabilities keep on decreasing. So sometimes blue is better than red, sometimes again here blue is better than red, but in long run blue goes down and red becomes better. So now question is that if a person individual perspective, if you think, so what should we do? Up to 12 months, obviously you are supposed to give that treatment, and after 12 months or 24 or 36 months, obviously you are supposed to treat the patients up to NLR low, but suddenly NLR high is becoming better than NLR low. The question is that what to, but when the patient is already given in particular high or low, you can't switch them into different part, because there is not any, that would be difficult, because there will not be any impact on that earlier doses or earlier effect. So the questions comes here is another way, another part of that, and there is a huge differences that in a better positions to make a comment that blue is or low is doing better than high. So that makes important to make the in what part of the curves we are going to make the comparison. So basically we are having two way to handle that work. One is the log rank test, that is more sensitive towards later survival curve comparison, and another thing is that Gehan test, that is more sensible towards early survival curve comparison. So we are having only two ways to handle that. Quite often we use the log rank test because this is that mostly used because we are much more interested about the final outcome or final comparison, and Gehan test is very rarely used because people are much more oriented or interested towards the overall survival curve comparison, but that's why the later survival comparison makes more sense than earlier survival curve comparison. But unfortunately, people for making this earlier curve comparison, people always use log rank test, and that is not the correct way to apply. So that's why Gehan test is there. So both tests works nicely, but it says that theoretically Gehan test is much more sensible or better to have if you want to look on the initial curve comparison. So how these curves are making comparables, and that story is now I'm going to come, and that also help us to make the survival, how we are going to make the survival probability over there. Okay, so let's say these 4 columns and how to are going to make, and this is the way inter survival analysis stand, and it is very important to understand because how the theory behind that works, unless and until you are having that clarity, it's very difficult to apply any statistical software and get the results. So that is the reason I'm doing. Earlier days people used to do with this hand, but nowadays due to this software availability, people can do the software. But thing is that it is very much important to understand the background, what happened. Then application of the software becomes easy and correct way than without knowing it. So let's say if you are having 4 column here, TJ, NJ, MJ, and TJ, QJ. So basically these are J are standing for the individual we are talking, or sorry, not individual. We are talking about the time points or the different measurements over there. So let's say the log rank test stand that we are observing the entire study into, or split the entire study into different time months. So first time months, like say 0, that will be baseline observations. First, so initial one there as a 0, thereafter first month to second month, third month, up to 23rd month, we are having observations of the patients. We are not talking about here any treatment wise comparison. We are talking about overall comparison. So overall patient, irrespective of the treatments are given, how the log rank is prepared, that's I'm going to present here. So let's say this is the observations. We are going to make the observations. And as we said that when we are talking about the patients and NI basically, or NJ is basically the number of patients who are treated. So since we are talking about all the patients are enrolled in a study, so at day 0 or day baseline, everybody should have their observations that is expected, and you are going to have that thing. So that's why N is considered here as a 21. So your study cohort size is basically 21, where we are started. So if you talk about study entry date, enrollment date, clinical trial start date, everywhere that this particular date must be there, or for all patients were recruited. So if you started with the cohort with 21, let's say, so all of them at baseline or at day 0, there all of them measurement would be there. That's why we are starting with the cohort size with N here as 21. Now see, slowly these values are keep on dropping, and somewhere 21, 21, 19, 17, 16, 14, 12, 8, 6, 4, like that, it's keep on dropping. Why? There are 2 reasons to drop. One thing is that basically the typical reason that the death as an event. Secondly, there is another reason that is called persons may be censored. So right now we are not going or censored or kind of story. So right now we are, to make the life little easy, so we are not considering any one of them are censored. So we are going to say that all patients were died. So that is a theoretically we are in a best position. So if somebody is censored, that can also be managed, and that place Q would be, if one patient is censored, then that Q1 would take value with 1. So right now we are not going in that details. We are only considering all patients are died or all patients have been observed with the event. So all patients event is yes. None of them are having no event is not there. So all of them are having event. So now at the baseline time point, we observe that none of them died. So all of them were alive. So that's why this part is survival of T, S of T is coming 1. So probability is coming at 1 value. Now that is fine. That is the probability that every curve we have seen until now. Every curve started with the y-axis with 1. That is a perfectly done. Now secondly, after having the 1 month observations, out of 21, let's say 2% died. Because out of 2%, how died? See, one person was having 15 days, and that after that patients died. Another was having after 20 days patient died. So 21, we started with the first month, we started with the 21, but meanwhile 2% died. So end of 1 month. So we started with 1 month, means that after we end with the first 0 month with 21. We started with again with the first month with 21, but during 21 means first day to 31st day, out among these 2 durations, 2% died. So we come down from rest, how many persons are alive? 2 minus 21, that is 19, and out of how many? 21. So that's coming to 90% survival. Now we are starting with the next month with 21 subtracted 2, that is because 2% already died. So that is going to down. So we started with the 19 people here. And again, in that month, also 2% died again. So we come down to 17. Okay. But this is basically 17 out of 21 is going to have that particular time point or particular month survival. But one thing is that this is, once I will go for the next slide, I will explain more. But let's say this is the typical survival. Those were survived up to 1 month, and out of them, 17 were alive again beyond 2 months. So 1 month plus alive, how many were? 19. 2 months plus alive, how many were? 17. So 2% died. So that durations from 1 to 2 months durations, the probability of survival is 0.8. Remember, so from 0 to 1 months, the probability of survival, or 0 days basically, if I say, so here it is 1, and thereafter, once the meter started reading, so from up to 1 month, it is 90%. Then 1 month to 2 months, it is 81%. Like everywhere, every month it is dropping. One question is very much important here, that what we are saying here, repeatedly I am saying that those were alive up to 1 month. How many were? 21. How many were? 19. 19 were alive after 1 month. So out of that we are going to make. But here, see, I'm putting it as a 17 by 21. Right? So this value basically considers we started with the 21 first. Okay. So if you calculate 17, so that's the here one conditional probability applied here. And that conditional probability basically multiplications with earlier time point survival with next time point survival, and that would give us that correct survival. So I would say here it is not basically the 17 by 21, it should be 17 by 19, again 19 divided by 21. Okay. Now, how to make that curve? Let's say you can just, I'm just giving some R code. If you are interested, you can look on that. It's a free software. You can download it and install it. So let's say time we are mentioned at the first time point, first individual time point measurement 1, second individual 1, third individual 2, fourth individual 2, like that. This number of individuals time we measure, and simultaneously we measure their status value like 1, 1, 1, 1. So all of them are died, we mentioned. Then you can mention that fit functions, and fit would give us, and then we can make the plot of that fit two functions, and we can get it. I will go little details. I will go for again once I will make the elaboration. So here we are going to make these curves. So softwares can make it very easily. So how it works now? Let's say how the conditional probability works here. So earlier we have seen that only those who are alive, those who are died, those contexts we consider. And now see, it is not, we are not in a position like everybody will be died and everybody will be having event. So in that sense, data could be having inflated with the censoring. So if your data which becomes with the censoring, how to manage it? So let's say here, every time the 3% died and 1% censor. So we started with the 0, then after 6 months, 7 months, 10 months, like that, these are the durations. And we started with the 21, and we keep on dropping on here. But here this number of patients are died, and here Q is basically the censored value. So how we are going to make this one? We are going to multiply 1 with 3 minus 21, that is 18 by 21. This is the first observation we are having. Now we comes down from 21 to 17, because 21 we subtract from there 4 persons are lost or moved away. 1 is basically due to the censoring and 3 basically due to the death or event. So it comes down from 21 to 17 here. And out of that 17, you see 1 person's died and 1 person censored. So the person died will be divided by, subtracted from 17. So we are going to 16 and again divided by 17 and multiplying with 0.85 because these are the conditional probability that is going to apply. So every time see, we are keep on multiplying the value and we are going to land with the new numerical value. But always see these survival values are going to drop down 0.85 to 0.8075, 0.69, 0.62, 0.53, 0.44. But still we are, even we multiplied with some value. So this is the entire story to get the survival curve. Start with the value, take how many observe, how many events are happening, how many are censored. So if you are no censor, no event, so your particular probability of survival is 1. Go to next time points, check out of that how many are died or event occurred or how many you are having censored. So here we are having 1 censored and 3 event, 3 subtracted from 21. That's all. You are going to get the 18. And then we started with the 21. That's why we are going to make the denominator as 21. And earlier time point survival probability need to be multiplied. That's why we're going to follow 1. And we are going to get the overall survival probability as a 0.8571. Return this survival probability again for next stage 0.8571. But go for 17 as a denominator here. Subtract 1 from 17 as 16 here and multiply. We are overlooking this 1 and 1 here. For what? For calculating the survival, because we know we are not considering the censored towards calculating the survival. Unless and until event is occurred or unless and until person is died, we can't consider that value as to calculating the survival. So here this 1 is overlooked here. Look, this 1 value is overlooked. So we are considering 18 out of 21. Where is this 1 gone? We just avoiding it, removing it for calculating. Similarly, this 1 subtracted from 16, so from 17. So that's why we land with 16 divided by 17 and bring the earlier survival probability, but overlook this value. Where do we overlook that value? We overlook that value with the next stage. So here from 17, if you died, it is supposed to be 16, but it came down to 15 because 1 died and 1 censor has already been taken care and it come down to 15. Similarly, from 15, you are supposed to get 14, but we are getting 12 because 1 plus 2 both been taken care here by making that 15 to 12. Similarly, the entire survival curves are made. So this is the 1 curves. If you talk about the treatment 1 and treatment 2, cisplatin with cetuximab, radiation with the chemo. So for particular treatment, we are going to make the 1 curves like that. For another treatment, we are going to make similar parallel curves that, and we are going to plot this value. So we started with the 1, then 0.85, 0.80, so 0.75, and going to plotting them. And then after that, we are going to make which point or which curves are better as compared to another curve. That's the way the entire story happened. We look at 2 groups, extension of the several group possible. So as we mentioned that we can make several curves with several groups or comparison, but eventually we only consider only 2 groups. That makes life simple to understand. When you have 2 Kaplan-Meier curves statistically equivalent, testing procedure compared the 2 graphs, we don't have the evidence to indicate that 2 survival curves are different. So null hypothesis says that no difference between the survival curves. Goal is to find out the expressions or dependent on data from which we know the distributions and approximately. So basically that if you are not in a position to make that final conclusions by the log rank test, then you can proceed with the parametric test approach. That I will come to the next presentations. So that's that how it happened. So basically 2 group of people are there, and corresponding to that both groups are observed at particular time point T1, T2, T3 by 23. And for all the particular groups there, we are having their event rate. Like for group A, we are having no event 0 0 0 0 and then 3 1 like, and event 2 or so group 2 there is having this number of event that happen, these are people are died, and this we are having, we can calculate the people at risk and we can make the comparison, and that's the way these are the mathematical formulae to calculate the derivations or to give us the expected cell counts value. And this is one kind of extension of the log-rank test. Is the if you have applied this simple normal statistics, summary statistics, then you might have heard about the chi-square test. So this log-rank test is nothing but the extension of the chi-square test in the survival context, where we are making this with respect to time. So here we are managing the time by different, we are managing by making the time into by splitting in different time points, and thereafter we are going to make the comparison. So as we see that here the expected cell values are created, and we are also having the observed value, and then thereafter we can make the log-rank test statistics comparison. So if this value is quite high, so then we are going to say that both groups are different. I'm not going more details about how to calculate the observed and expected value, because nowadays nobody calculate manually, so it makes no sense. But basically we are going to make that difference between these two groups by looking this value by log-rank test value. If this value log-rank test value, is a numerical value, if this numerical value is quite high, that's mean the difference is quite large between the two treatment group, then we have to have the hypothesis is going to fail. So reject the null hypothesis, and we are going to state that one group is survival is different than another group. If this log-rank test is very nominal, it's near to 0, that's mean we are going to say, or this log-rank test is not very much different. So that's mean groups are not very much different, and they are survival difference or survival over the time point is makes sense, or it's in similar way. So as I mentioned, log-rank test is nothing but the extension of the chi-square statistics. If we apply chi-square statistics in 2x2 cross-tab value, there also we have seen the how to apply the chi-square statistics. So this is the extension of the chi-square statistics of the log-rank test, and we can apply and we can get the results. How to do with the R? That's a simple lines you can apply. So basically, if you time is given, so all the individuals time of measurement, simple data I'm just prepare here. So if you give 6, 6, 7, 10, 13, 16, 22, and status is given as 1, 1, 0, 0, 0, 1, 1, and treatment is given as 1, 1, 2, 2, 2, then we can make the function called SURV with capital SURV, then time, comma, status, and thereafter treatment. So these functions applied available in R with the library called survival. So that library called survival can be used to get this value, and thereafter we can call the fit functions. The fit, if you make, then we are going to get the p value as 0.2. All short of analysis are going to, even if you do the SPSS or SAS, any other software, all software are going to give you these kind of results, and you will get the observed minus expected value everywhere. But here the chi-square value ultimately going to give us, and that is also coming with the p value with 0.2, and it says that there is not any difference in this our illustrated result here. Okay. Similarly, another data example in library survival, there is a data called lung data is there. You can call the library survival, and thereafter you can call the lung data, and in the lung data directly you can apply these functions, and you going to get, in that case you are going to get the p value is 0.001. So it's going to say basically there is a big difference between these two graphs. Now comes to the second one, what is called Gehan test. Gehan test basically makes the order of the two samples. So if we are having observations of one group of patients as x1, x2, and xn, and second group of patients we consider as y1, y2, and yn, then order the value in the order statistics. Basically, it's applied as order statistics, and thereafter similar fashions we make the difference between R1 and R1 and ER and square root by variance of R1. So basically ranking mechanism is applied here. So rank of xi is applied, and thereafter the summation of rank is applied. And then we assume that this value, the ri minus er square root by variance, is going to follow the normal distributions. And if it is if this value is quite large, then we are going to say this is rejecting the null hypothesis. It is low, then we are going to accept the null hypothesis, and that's the way the entire story works. If reject the null hypothesis, if R1 value is too big or small by, so it might happen. So see here also we are going to make R1 minus ER by dividing by some square root value. This is for Gehan test, and we have seen here this is the Lagrange test. So we are making the difference of O2 and E2 and by dividing the var value. So that's the data, how we are going to calculate mean value, square root value, and how to put them, manipulating them to calculate the expected value. ER basically the expected value, and var is basically the variance value. That makes the difference to calculate the Lagrange test and Gehan test over there. Once that is done, the very simple methods, simple functions, or very useful library I would say is there called PH infinity estimates. So but people commonly use by default, people without looking the data, without graphical exploration the data, people use the Lagrange test. That's not a correct way approach to apply. So if you say that your data is much more approachable for Lagrange, definitely you can proceed. If it approachable much more with the Gehan test, then you can go with the Gehan test. So then Gehan.Wilcoxon.test function is available. Again, like subdiff work here, like Gehan.Wilcoxon.test work, and thereafter survival time, censored, followed by G. G is basically that arms wise comparison we are talking. So you can take as a G can be considered as an arm. You can consider G as gender. So G can be considered anything, and thereafter you have to call as a data equals to brace. So base example data is also available in that package. So you can download that package. You can download that data. You can see how the data should look like and apply with the time with the censoring. And that data, that result would give you the p-value again with the 0.00095. So that's p-value quite significant, less than 0.05, and we can make a statement that okay, there is a huge difference between these two groups. So this is basically the Lagrange test and Gehan test. And while again there is a two-way. So one thing is that making the comparison by numerical value, and another thing is that making the comparison by survival curves by looking at explorations. So while you plot that, we can get a conclusive idea about that which groups are doing better as compared to another group. But numerical, while you are going to have the numerical evidence, so for that evidence, Gehan test and Lagrange test are very much useful, and we can apply in that direction. So I'm not sure about the spaces is having that, or another costly software is definitely the SAS is having Gehan test or not, but you can easily get it in the Lagrange test and Gehan test in R. So with that, I would like to end here with my this presentations, and happy to have some any comments or any questions on that. So